Okay, so this is the slides for week 9. We're going to talk about memory architecture. We're going to talk about the role of memory, memory organization for programs, and also memory hierarchy. So in embedded systems, there are many memory components. Beyond memory component, there are storage, communications. We need to communicate with sensors and actuators. We need to do computing, but it's with more constrained resource than general purpose computing. We have to have the system in a small form factor, consume very little amount of power, low power consumption, and very reliable. We use memory for all kinds of stages or parts of the design for storing instructions, for storing data, sensor data, input data, and also for storing data that will be used to control the actuators. And for signal processing or any processing task for the computation, we need memory to store intermediate variables. So memory is very important in the embedded system. We will consider many different things as part of the memory architecture. We will consider the types of memory. Is it going to be volatile or non-volatile? And for volatile memory, is it going to be SRAM or DRAM? Both have pros and cons. For SRAM, it's faster than DRAM, but SRAM tends to be costly. So that's why we tend to have smaller size of SRAM than DRAM. And DRAM could be abundant with large quantity because it's cheap. We also have issues about memory maps. Hardware architecture is the ones used very often by embedded microcontrollers. And memory mapped I/O, like the memory map we showed earlier, some of the registers can be mapped to both. The I/O registers can be mapped in memory address space, and you can access them either way. Also, we consider memory organization. Some variables or data are statically allocated. Some are allocated in stacks. Some are allocated in heaps. And also related to that, there's different memory model of C programming, and also internally how we organize these memory and caches and virtual memory, etc. And then in the protect environment, we also consider the memory segmentation to isolate processes. All right. So for non-volatile memory, essentially preserves contents when the power is off. You have been using it a lot. The USB thumb drives, those are type of non-volatile memory. There are even more finer categories, EEPROM and double EEPROM. Those are the programmable read-only memory used in computer motherboards and many other places. You basically program once, and that information will stay there. That's very useful for things like bootloaders, BIOS. And for flash memory, you can read and write. You can erase a block at a time. It can endure a large number of erase cycles. and the controller can be quite complex. And then for disk drives are also possible, but it's not well suited for embedded systems due to the power consumption form factors. So flash memory are the most widely used type of memory in embedded world if you want to store information for longer term. And if you do want frequent read-write, then you're going to be looking at different types of memory. And that's the volatile memory. Volatile memory, you can read and write at the runtime as you need, but they will lose contents when power is off. In this category, there are SRAM, DRAM, also for SRAMs, it stands for static random access memory. It's very fast among all these different types, but it's more power hungry, and they are used only for small storage units like caches, scratch pad, things like that. DRAM is more popular because it's cost effective. It's slower than SRAM, but you can pack a lot more bytes in a single chip than SRAM. It requires some periodic refresh, typically used for main memory. For bootloaders, they will transfer data from non-volatile memory to volatile memory, and then the system can go on from that point. So normally, if a desktop or laptop, we power it up. Sometimes the vendors manufacture the logo flash, and then you can see a few quick messages pop up before your OS loads, and that's the bootloader, which basically loads the OS from a non-volatile storage space and then put them to volatile memory like DRAM, and then the system can go on from that point and running on these volatile memory. Here's an example of the chip with ARM core and 1 megabytes of flash memory. So memory maps are very typical for all different embedded systems. We saw the example of AVR microcontroller earlier. This is an example, so don't take the numbers literally. In this example, we have a few segments in this big memory space. So if you count from 0 all the way to 8 Fs, that's actually 4 gigabytes. And it's segmented to program memory, data memory, peripherals, data memory DRAM, external devices, and so on. It's easy to mistaken that you have all these, or you have to have all these resources. This memory map is just to say that if you want to have some data memory, like DRAM, to be used by the microcontroller or microprocessor, they should reside in this memory region. Doesn't mean that you have to have the full segment allocated to the physical memory. You don't have to have that big of DRAM chip. But if you do have DRAM space, you should allocate them in this place. So that would determine how you do the memory decoders, address decoders, to make sure that when the microprocessor accesses this address, it will be able to access the data in the DRAM chip. Some history about AVR, which is an 8-bit single chip microcontroller. It was developed by 2 students from Norway, and it carries a lot of success. It has a modified hybrid architecture. That means using separate memory space for program and data. Arduino is the open source hardware boards that use AVR processors from the beginning. It has a lot of variations since that point. And there's good people in the open source hardware domain. This founder of Arduino and also the founder of Adafruit, which is a very good company that designs, builds, and sells maker gadgets, electronics. Another example using AVR processor, that's the controller board for the iRobot, the automated cleaner machine to clean the floors. Okay, this is another Atmega chip using AVR architecture. This is an 8-bit microcontroller with 16-bit address. So there are several things that we want to point out here. This is the ALU, which stands for the CPU. And we have general purpose registers. We have 32 of them. Each of them is 8-bit. And we have 8-bit data bus that connects to all these different components. So connects the ALU with the memory, the data memory, also the EEPROM, and program counter. And that connects to the program memory, which is based on flash. And the instructions will be read from that program memory and decoded and then sent to the control so that the ALU can perform certain actions. This is an 8-bit microcontroller with 16-bit address. 8-bit because the data bus is 8-bit, and also the data width of the registers for the CPU to do computation, they are all 8-bit wide. 16-bit address because, as you can see, the addresses to these memory locations, they are 16-bit wide. You have 4 hexadecimal digits, starting from 0 to 04FF. Depends on the different processors that you actually use. So the question, why is it called 8-bit microcontroller? Is mainly because the ALU takes 8-bit values from the general purpose registers, and all the general purpose registers are 8-bit wide, and also the computation, the data bus is 8-bit. Flash memory is for storing instructions. So when you program, the instructions generated by the compiler will be put into flash memory, and they will stay there until you program it again. So it will stay there when you power off. This data SRAM is where you store the general purpose data that you can use to use it to store any temporal variables that you use in your computation, in your program. Additional I/O on the command module. So you have the timer, interrupt, and the PWM channels, ADC, and so on. All right, so that was about some terminologies in terms of memory types. In the next few slides, I want to talk about memory organization for programs. Specifically, we're going to look at the different ways to allocate memory and use memory. One is statically allocated. That's when the compiler choose the address at which to store a variable. For stack is dynamic allocated memory with last in first out strategy. Heap is dynamically allocated, mainly for the system applications. First example, statically allocated memory in C. So we have a few lines of code. we have a main program, and that's int main, no input arguments. And before that main function, I declare variable x, which is type of character. So that's 8-bit. And in the main program, I assign 20 to x. I mean 20 in hexadecimal. So what we see in this example is that we have one variable that's x, and it's declared outside the function, and in fact outside the main function. And it's a so-called global variable in the C programming. And this case, the compiler will choose what address to use for x. And because it's declared outside the functions, so this variable is accessible across all the functions, all the procedures. This variable's lifetime is the total duration of the program execution. So that's what we call statically allocated memory in C. We can also statically allocate a variable, memory space for a variable with limited scope. In this example, we have a function full, and inside a function, I declare a variable x again, and its character type. But before that, I have a keyword called static. So this static will make sure that this variable, even though it's declared inside a function, it will be allocated in a statically allocated memory, so that it will retain its value even after this function ends, or when you get out of the function. So the compiler will choose what address to use to store this value, but this variable is meant to be accessible only in full. The purpose of the static is to make sure that the lifetime is the total duration of the program, so that when you call this function the next time, this x will return its value. Now, if we don't have a static declaration before the type, so we have our character and type variable x. In this case, this variable will be an automatic variable, and this variable will be allocated on the stack. So the stack is where the procedure or the function maintained. It's a space that will be allocated when you enter this function, and a space will be deallocated when you finish this function, so when we exit from here. When the procedure is called, this variable is assigned an address on the stack by using the stack pointer. So somewhere here, you maintain a stack pointer. This variable will take one space, one byte here, and then you will be able to use that space to store the value of this variable during the execution of this function. This variable persists only for the duration of the call. So when you exit this function, this stack segment, a few words or a few bytes will be deallocated, and this value of this x will be gone. The stack is somewhere here. As you call the procedure, if it is nested, that means you call the same procedure again within the procedure or within the function. The stack pointer will move to a lower address space, and when the procedure returns, the pointer will move up. So you can call functions, one after another. You can call a function which can call another function, and so on. So that's how the stack grows and shrinks when the functions exit one by one. So in the next few slides, I have a few questions, and I would like you to think to answer the questions related to the memory allocation for these variables. The first question is based on the program here. We have character x, that's how we declare this variable. And also we have a function foo, and inside the function, we assign 20 to x. So with this program, when this is the way we declare variable x, what will the compiler do? How will we allocate memory space for this variable? What is the implications of this? Specifically, what is the data width of this variable? Is it a byte or word or 2 bytes or some other size? And the other question
1 byte.
Is 1 byte. And the other question is specifically where this variable going to be stored. Is it going to be in statically allocated space, or is it going to be in a stack, which is part of the managed by the function, by the procedure?
It should be statically allocated space.
That's correct, because we declared this variable outside the function or procedure, so this will be a 8-bit quantity that's in the statically allocated space in internal memory. And of course, the exact location will be determined by the compiler because chances are there are more than one variables in that space, so the compiler will arrange them one by one. The second question, we have a slightly different program here. We have the same foo function, and the way we use x is the same. However, when we declare this variable, we declare as a character with this heuristic and x. So same questions. What is the size of this variable going to be? Where is it going to be stored? Is it going to be statically allocated space, or is it going to be on the stack? So first of all, what is the size of this variable? Is it 1 byte, or 2 bytes, or 3 bytes, or 4 bytes?
Still 1 byte.
Okay, where is it going to be allocated?
It's going to be allocated at address 0x20.
Okay, so this is a much trickier question than the first one. So we kind of agree that this is going to be, again, in a statically allocated space, but we disagree on the data size, and also we probably disagree on the value of it. So first line here, character heuristic and x, in the C context, in the C programs, this is where we declare x as the address that points to a variable of type character. So x itself is an address. And with this address, we can find a value that's of type character, that's a byte. And because in this processor, the memory space, if you look at this memory data memory map, the addresses are all 16-bit. So the possible value of x is actually 16-bit. That is to say, if we want x to be an address, which we say that here, x is an address, then X itself should be 16-bit. Does it make sense? Do you follow?
Yes, that makes sense.
So this is different from the previous question or example. Here, X itself is a 16-bit quantity because it represents an address. And in our case, this processor, the address is a 16-bit value. So X itself is a 16-bit quantity. And this variable X is stored at an address in the statically allocated memory in the internal RAM determined by the compiler. So this variable is somewhere here, but this variable is a 16-bit value. And when we go into this function, you assign 20 to X. That is to say, oh, this address now assign it to 20. So we'll later can use this address to find the corresponding value at that memory location 20. And that's likely to be here. But X itself is a 16-bit variable that's allocated in this memory region by the compiler. Okay, question number 3, we are adding one more variable, y. So, for X, it's the same. What about Y? What's the, is Y a 8-bit value or 16-bit? And where is Y going to be allocated?
So Y will be 8 bits.
Correct?
And
And Y will be also in the statically allocated space as X. Okay, one more question. So we have full function, and inside the function we have characteristic X comma Y. And outside the function we have character Z. So where are X, Y, Z in memory? So we have two options, whether are they in statically allocated memory or are they in stack?
X and Y are in static. X and Y are in on the stack, and Z is in statically allocated memory.
Yep, I would agree with that. And again, X occupies 2 bytes, Y and Z occupy 1 byte each, and X, Y are on the stack, and Z are in the statically allocated memory. Oh, there's one more. Okay, so what is this? What are we doing here? So I have 2 variables because they are declared inside the function. So both of them are going to be on the stack. So they will be allocated when you enter this function, and they will disappear when you exit from the function. Again, X is going to be a 16-bit value because of its address, and Y is a 8-bit value on the stack. And this line here is to get the address of y and assign that to x. This is the ampersand sign is for. And this x is to assign 20 to that location. So do you know what the value of y is going to be after this line?
A 0x20.
Correct. Yeah, because x points to exactly y. So when we assign a new value using x as the address, we essentially assign 0x20 to variable y. Okay, we have one more. What goes into Z in the following program? Okay, so Z is the return value of this full function. So we have in this function, we declare y, which is 1 byte, and we declare x, which is 2 bytes. And we put x to 20 hexadecimal to x. And we will use that address to get the value of it. So we're actually reading something from that location and put that return value, put the value that you read from the address 20 to y, and then return y. Right, so that's what we do exactly. So we're gonna load the value from IO register at location 20 and put the value into Z. Okay, I will skip this one. Oh, what happened? There's also some tricky things about recursion. You can call the function, the same function itself within the function. Of course, you need to set a end condition. You can try this interesting example. Also, for dynamically allocated memory, we have heap. So heap is what the OS manages. It's a way for using the memory more efficiently or under programmer's control. When you have calls like malloc and free, those are for programmers to allocate a certain amount of space, not just for one variable, but for continuous segment of the memory. Use that for some.
Okay.
For
sorry that I wasn't able to get my charger to you. I forgot my mom had bowling right after work.
Someone please mute.
Time to bring it. So, sorry, but I'll make sure I take it out as soon as I get to the house for tomorrow. Okay.
Okay.
Can you please mute yourself? Okay, so with this malloc and free, you have the flexibility of using memory more freely, especially for a big chunk. But if you don't do it carefully, you may lead to memory leak problems. For example, you do malloc, memory allocation for 1 kilobytes, and you do that for 1,000 times. And that means you're allocating 1 megabytes of space. After you use it, you can call free, and you should call free to release those allocated space. But if you miss that, then you basically take control of this 1 megabytes forever until your program dies. If you do that very frequently, you're going to be accumulating these unused memory, but allocated, but unused, never freed. Eventually, you're going to use up all the physical memory in your system. Also may cause memory fragmentation that will prevent you from allocating larger space if you don't free enough space that you requested earlier. There's techniques about how you manage this more efficiently, automatic garbage collection. It requires stopping everything and reorganizing, but that's not really very useful in the embedded domain, especially for real-time programs.
Okay. So we have a few slides left from last week regarding memory architecture. So we're going to cover those first. We talked about memory architecture, how the microcontrollers organize memory spaces, and how do we locate the ports and data in the memory, etc. Here we're going to look at memory hierarchies. Memory hierarchies refer to the fact that you have a few different types of memory in an embedded system. Typically, you have register files, sometimes called scratch pads. In addition to those, you have caches. That's more common in higher-end microprocessors, embedded microprocessors. Caches is a subset of memory space that's mapped to SRAM. So because it's based on SRAM, its access speed is fast, but the size of the cache is relatively small. If you access any item that's stored in this SRAM using an address, you may or may not find that data item in this space, so-called cache. If you are using an address trying to find data, but that data is not in the cache, that's called a cache miss. A miss is handled by copying contents from the larger DRAM to SRAM. Scratchpad is a little bit different from cache, even though both Scratchpad and cache are based on SRAM. Scratchpad is using a separate address space from the DRAM. In contrast, cache shares the same address space, even though cache is much smaller than DRAM. So that's a major difference between the cache and Scratchpad. And for cache, you don't really have to manage. It's built in the microprocessor chip. It's addressing, it's invalidation, or copying data from DRAM to cache if it is not there. All these are done by the microprocessor hardware, the chip itself. Whereas for Scratchpad, it's essentially a small but fast memory space that your software can use. So your software manages what is stored there. Segmentation is a way to maintain multiple regions out of the same physical space for different purposes. And oftentimes you use segmentation to organize data for instruction, organize information such as instructions or data. And you may have segments for different tasks or processes. And you will need to use permissions and also the roles to regulate which task can access which memory. All right, this is an example where we have cache in addition to the main memory. what we have here is a CPU that's gonna do computation on data. The CPU will be doing computation on data that is stored in the registers, and registers or register file is on the same chip as the computing unit, and it's part of the CPU. You can access these data and very quickly. So the instructions will be able to access them, do the computation, and store the results back to them. But because registers are limited in the processor, so you have to use a larger memory space, cache, and then DRAM. Now this diagram doesn't really show that well where the cache is actually part of the CPU. That's the reason that we say cache is managed by the CPU hardware, and you just really don't have to worry, how do you manage the data in the cache. And this part, if it is a scratch pad, then it may or may not be on the chip, but more cases it will be also on the chip, on the microprocessor. If you go further from the CPU, you will see you use a larger memory component based on DRAM. DRAM has a higher density, but it has to rely on refresh to keep the information alive or retain the information. And cache is part of the DRAM address space. So when you access data, you supply address from the processor to these memory components. If the address you're trying to access, the cache has a copy already, then you can get the copy and fetch the data directly and then do the computation next. If you cannot find the data in the cache using the address, then the processor needs to go further to access the main memory, where for sure you should find the data that you want to access. Even further away, that's the secondary storage based on magnetic disk or non-volatile flash, where you can store a larger amount of information for a longer time, even after the system is powered off. This diagram shows a little bit differently, where your SRAM-based scratch pad has a separate memory address space. So you need to have specifically different addresses to access the data in a scratch pad. For data in the main memory, you need to use another separate different address. So you will these components will own has its own segment of address space. In these situations, you have to really design your software well so you can take full advantage of this scratch pad, because now this scratch pad, this fast memory, is under the software control. It's up to you how to use these. Next, a few slides about cache and how it's internally designed to be able to store a copy of data so that you can access them quickly. What we see here is a very simple illustration of a direct mapped cache. We'll see, if it is not direct mapped, how we organize them. But for the direct map case, what you see here is this is the SRAM-based cache. You store information, some data, and the data is actually in this block. And you can use 2 to the power b bytes per block. Let's say if you choose b equals to 8, so you're talking about 2 to the power 8. So that's 256 bytes. in this block. Now this B is actually a part of the address that you use to access data. This address comes from the microprocessor, and depends on the processor. This address could be 8-bit address, could be 16-bit, could be 32-bit. Typically, it's 32-bit address, and now here, let's say this little b, small b is 8, so we're talking about 8-bit out of the 32-bit. Then this is the part of the address where we use to find the individual bytes in this block. Because in this block, we have exactly to the power of b bytes data here. And then on the next set of bits is called set index. Set index is the bits we use to find out which set we're going to be looking for the bytes, looking for the data blocks. So it depends on how many bits we use here. Let's say if we have another 8 bits. So we have 8 bits here for the block offset, and then we have another 8 bits for the set index. The set index, because it's 8-bit, so we're really talking about we have from set 0, 1 up to set 255. So altogether 256 sets. So with this 8 bits here, we can find out which set that we're going to be going into to look for that block. Okay, so now you may wonder, then you have another maybe in our case 16 bits left, because let's say we have 32-bit address, we have 8 bits here, 8 bits here, then the tag, this part will be 16 bits. How are we going to use this 16 bits? Now, if we have a data in, let's say, this set number 1. Okay, let's say this 8-bit, we have 00000001. So that's going to be set index 1. So that will, guide us to this set. Do we know if the data we're looking for is here or not? It might be there, but it might be not. The only way we can tell is to compare the tag that's stored as a part of the data block with the tag with the remaining upper 16 bits from the address. If this tag matches this tag, then we say we have a cache hit. That really means that the data block we're trying to access using this address is here. Okay, so it's let's say if you access a byte and you give this address, so and if this tag matches, then we're going to be using the lower 8 bits from this block offset to find the byte that's in the block. So if you have the lower 8 bits as, let's say, 00000010, so that's 2. So then that byte is here. If we say this is byte 0, byte 1, byte 2, so that byte is going to be here. Now, if when we compare the tag here and here, they do not match, or if we see this flag is set as 0, which indicates it's invalid. So that means the data block we're trying to access is not the ones that's already stored here. And that's called a cache miss. When we have a cache miss, we will invalidate this block. So we're going to be kind of discard whatever is here. and then go to the lower level of memory hierarchy, that means the DRAM, to load the real block, real bytes here to fill this up, and then put a tag here and mark this as a valid. So why do we do that? Because the next time, if you access the same address, you will sure find this tag will match with your address's tag, and it's a valid block. So your data will be here. And that's really the benefit of having a cache, so that we will be able to store the frequently used data in this fast SRAM, and to save the time from accessing the DRAM again and again. Do you have any questions if I move on to the next? All right, so in the first case, we were talking about a direct mapped. And here is the, it's a little bit different in the sense that in each set, we may have more than one blocks. So in this case, we have 1, 2, or maybe more in set 0. And then we have another set of blocks in a different set 1, and so on. So this will give us some additional requirement, because when you use this set index to find the set, you will need to compare the tag with a few of those here in the same set. And for sure, there will be one matches if there's a match, because all these tags should be different. And if there's a match, you declare that's a cache hit, and then this block here is the data that you want to access. If there's no match, okay, none of these tags stored here matches what you have in the incoming address, then guess what? You need to replace one of those with this tag. And by replacing, really mean that we have to go to the DRAM to fetch the corresponding block, put the real data here, update this tag with the address you are using, and then mark this as a valid. Okay, so the tag matching is part of the process for the set associative cache, and it's done usually using associative memory or content addressable memory, so the matching can be done quickly. We mentioned earlier that if there's a cache miss, you need to replace one of these existing blocks in a set. You can use policies like least recently used or first in, first out to replace one of those existing blocks in the set. Okay, so that was a very quick introduction about the cache architecture. You probably learned a little bit about cache in your computer architecture course if you're taking one or already took one. So overall, what we covered so far was the memory architecture, how we use software to access data, also how do we manage the memory in high-level programs, and internally how these memory hierarchies are implemented. So far, all the programs that we have seen or we've written, you don't really talk about timing. Timing is not part of the software semantics. When you write a software, what you really care about is the correct execution of the program. No matter what languages you use, your program has nothing to do with how long it takes to do anything. Of course, there are exceptions when you use time-related functions specifically, but most of the time you care about the correctness of the program. So all the computation and networking abstractions are based on these premises. And when you execute a program, if the program takes advantage of the cache hierarchy, you can benefit from it if your data is already in a cache. But on the other hand, you really don't know how quickly or how slowly your program are going to finish. Particularly if you have a lot of memory access instructions, you will have very hard time to predict or calculate exactly how long your program going to take, because the memory accesses may take shorter time if the data is already in the cache. But if the data is not in the cache, then longer memory access latency is expected. So that's why we say caches improve the performance at the expense of making it difficult to control timing. So that's kind of the downside of it. And in some situations, you may need to know exactly or control exactly how quickly your instructions or program finish. In that case, you have to be mindful about the underlying cache architecture that may influence the execution time. So we talk about memory architecture, which is essential to programming embedded systems.